the screen went black all of a sudden. Apparently the stream dropped and my laptop helpfully hid the notification from me because I was in full screen mode. So I didn't realize that that happened. So I changed that setting and hopefully things will go well. It looks like the stream has started for that. So, and I'll get my window, the share screen here. There we go. We have a question. Um, Can't come to office hours, but questions about if and how to center and what should come after model GLM. Um, so is that in the context of section 1 of homework 4 when we're talking about the 4 groups? Okay. Um, do you want to enter questions now or talk to me later? Okay. Just, okay. Yeah, we can. I try to be. Yeah, so just to remind you, for those of you who weren't able to join us last time, on Tuesday, in the context of going over formative assessment number 5, I also went over the coding schemes to do the first part of homework 4, the section 1 where we have the 4 groups. The only thing I didn't give was how to get the group means, but you had already done something very similar at the end of homework 3. And so that same concept should apply, but let me know if you have questions about that. Otherwise, let me see here. We get that out of the way. We can go back over the quadratic stuff that we started last time, since the stream didn't capture that. Does that sound like a plan? Okay. So more generally, what I'm trying to give you is ways of getting predictors into a model to capture different types of associations. So in the beginning of the semester, when we covered bivariate associations, for instance, they were sort of two kinds. You can either say that your variables are quantitative, and then you would have a correlation between them, but that correlation only captures a linear relationship. Um, the same thing is true of a Spearman correlation. It's a linear relationship between the rank orders, but not all quantitative variables would be expected to have linear relationships with each other. So what we're talking about now is other kinds of relationships that a quantitative predictor can have in predicting a quantitative outcome. Two kinds in particular that follow along with sections 2 and 3 of homework 4. One is quadratic effects or curvilinear associations, and the other is the piecewise stuff. And that's what Melissa was asking about that we haven't gotten to yet. So I'm starting on slide 21 of lecture 4. We did some of this last time, so I'll just review. So these are the types of associations that this lecture has in terms of examples. The one that we started talking about last time is quadratics. So it's also known as a parabola. It looks like a U if you were to graph it out, either an upside down U or a right side up U. And it's the idea that you may have a relationship that's positive up to a point, but the relationship becomes neutral, and then at some point it turns negative. An upside down U would be the same thing. It would start out negative, go to neutral, and then go to positive. And when you pair a linear effect of a predictor with a quadratic, then you can create all kinds of patterns, not just a regular U, but sort of tilted U's. And that's where the pictures that I had here came in. So these are just examples. Basically, quadratic effects, there are only 4 kinds in the world. You start with whatever the slope is for the linear term. So for instance, in this picture, what I have on slide 24 is effects of time. So in a longitudinal context, people may grow at different rates. So if I have time in the model as a predictor, that's what's known as the linear effect. The quantitative predictors that you've looked at in homework 3, those were linear effects. That's sort of the default. If you add the same predictor squared, so multiplied by itself, that's what's known as the quadratic effect. And those two predictors work together to create a function that has curvilinearity. The type of function that you can have, there's only 4. You start with whatever the linear slope is. If it's positive, the quadratic's job is either to speed it up or to slow it down. So I would call that more positive if it's speeding up or less positive if it's slowing down. So in slide 24 here, let me maximize this. There we go. Can you all see that? Slide 24? Okay. And the giant pink mouse, at least it looks giant to me. No, you can't see that? It looks tiny. Yeah, I forget I'm on a TV monitor. It looks ginormous, but I did that on purpose because I kept losing it, as I said. So in these functions, its time is centered such that the first occasion is the 0 point. So it starts at time 0, then time 1, time 2. And that way, the linear slope, the effective time by itself, is the effective time specifically at time 0. So in this top left-hand picture, the linear slope at time 0, the slope of the line that's tangent to the curve here, the little dotted lines, that is 4. So at that point, for every 1 unit increase in time, the outcome is supposed to go up by 4. When paired with a positive quadratic slope, so that would be the coefficient in the model that goes with time squared. That's the quadratic slope, the coefficient for time squared. In this function, it was positive 0.3. So what happens is that it takes that linear slope that's positive 4 and it makes it more positive for every unit in time by twice the quadratic coefficient. Homework question. Twice. That's the magic number. So at 1 unit in time more, the positive, go ahead. So the equation that created these, let me back up, would be like this right here. This is slide 23 before. So I have an intercept of 50. That's what the outcome would be at time 0. If x is time here, the slope is positive 4 for that variable x, and then the slope for the x squared variable, which would be time squared in this case, is positive 0.3. So this equation right here is what creates this first line right here. Twice. So the way to interpret these coefficients, the quadratic slope, the job of it, because it's a higher order term in the model, it's x is nested within x squared. Its job is to take that effect of x and make it either more positive, less positive, more negative, or less negative. And the way that it does that, you have to multiply the coefficient for the quadratic slope by 2. So if this quadratic slope coefficient is 0.3, it makes the linear slope of x more positive by 0.6 for every unit up. And there's two ways that I can explain that. One of them won't make any sense yet because we haven't talked about interaction terms, and unfortunately the pandemic forced those out of our curriculum this semester. But the other is, if you remember calculus and working with first and second derivatives, what we're talking about is the second derivative of the function, where the squared term comes down in front to multiply that variable. If you don't remember calculus, that's fine. I don't remember most of it either. I just remember this one handy rule. So you can, yeah, like I remember finding derivatives, and it's like you take the exponent and you bring it in front, right? That's my memory of it, and then you do it again, like until there's no more left. Um, so this quadratic coefficient that's in the linear equation here, it works out to be half the rate of acceleration or deceleration. So to get what the actual rate is, you have to multiply it by 2. And Cyril says, yes, so 0.3 times 2 is 0.6. Exactly. So if we play this out, so the slope of x, which is time in this picture here, the predictor, is 4 at time 0. That slope itself becomes more positive by 0.6 for every unit time. So the slope was 4, now it's 4.6, now it's 5.2, now it's 5.8. So this is acceleration. Unfortunately, this is COVID rates in Iowa right now. Sorry, real world example. It's not just bad that there's a lot of people getting sick. It's more bad that there's a lot of people getting sick because there's the rate of sickness getting is increasing, right? The problem is expanding every day. And that's why we're still on here and why we're starting our 6th week in quarantine, I think. And my son is still alive. I'm happy to report. So, we had some close calls, I gotta say, but I think I deserve a trophy for not hitting him at all, not even once. Any other parents here get trophies for not murdering your children yet? Yes, correct. Or your partners, or your pets, or yourselves, right? We're all a little crazy right now. And this is my one chance to be normal every week is to sit here and talk about quadratic coefficients. So hooray for that. But yes, COVID cases, accelerating positive. That's one type of quadratic. So this would be a linear slope that becomes more positive over time. Another type in the top right column here is a less positive. Now, this is what we want to see happen to COVID cases, right? In this case, the function is created from a negative quadratic coefficient for the x squared term. Yes, if you have to smell it and get a second opinion, I'm pretty sure that means don't eat it. There was a Saturday Night Live sketch about that. Like, is this milk bad? Smell it. Right. Yeah, no, if you need a second opinion, that it's no good. So, yes, thank you for sharing. Anyway, negative quadratics. This is what we want to see here. So the slope at time 0 is the same as in the left picture, right? The function is starting out at the same place of 4. But now the quadratic slope that's going to multiply the x squared variable in the function is negative. So the function has a slope that's becoming less positive as time goes on, and it becomes less positive by twice the quadratic coefficient. So it starts out at 4, but now it's 3.4, now it's 2.8, now it's 2.2. And this is the flattening of the curve, right? We want to get to a point where there's no more new cases in a given day. That's the goal. And that's when it will be safe to go back to classes and such, hopefully, and to get our haircut again. Yeah. Everyone's looking very shaggy. My brother apparently let his 10-year-old daughter trim his hair. He now has a mohawk that's crooked and has a permanent hat on his head for meetings and Zoom. So it could be worse. Um, all right. So is this making sense? This whole like less positive, more positive idea? Yeah, it's the terms work together. And so if one term is positive and one term is negative, then they're working in opposition. So in this case, up top right, it's the linear slope is positive, the quadratic slope is negative, and so it's taking that positive slope and slowing it down. The opposite is happening in the bottom left here. This is a negative linear slope with a positive quadratic. So now it's negative and it's becoming less negative. So if this is a decline, the rate of decline is itself slowing down. Because eventually it's going to switch directions. So what's constant is how the rate, excuse me, what's constant is how the slope changes per unit of the variable. That's what's constant. So how the linear slope changes is constant across the function. The linear self itself is not constant. It's going to either start out positive and flatten and eventually be negative, or it's going to start out negative, flatten, and eventually be positive. But the way that happens, the way the linear slope changes is constant. It's twice the quadratic per unit of the slope variable. Okay, does that help at all? No? Okay. These curves out, right? Like this bottom one here. It's negative zero point 0.1 or negative 1 by the time you hit time 5. Then it goes to negative zero point 0.4, and then it's going to become positive 2. Like, so it's going to change directions because as you head along the number line, like eventually if you're in negative side, you're going positive, then it's going to end up as a positive slope. If you start on the positive slide and you're going negative, it's going to end up as a negative slope. And the ones that are these acceleration pictures, like you don't see what would happen if you went to the left. So like if you went into negative time, that slope would eventually become negative, and then you'd be heading back up the other side of the curve. So like these pictures are showing really 1/2 of the potential U shape. Where you would get the full U shape is if the linear slope for the mean of the predictor were 0. Then you would be starting at 0 in the middle, and you'd either see this shape come out or the opposite. So it's pretty flexible in capturing a lot of shapes. So it's sort of curvilinear generally construed because it doesn't always take the shape of a U within the span of the data that you have. But if you've extrapolated beyond your data in either direction, then you would see the full U shape come out eventually. So you will have a question about this on your homework. You have to pick between more positive, less positive, more negative, less negative. And it just depends on what the linear slope is as your starting point. If the linear slope is positive, then it can either be the quadratic makes it more positive or less positive. That's it. If the linear slope starts out negative, then the quadratic slope makes it more negative or less negative. So you can narrow down the choices by knowing where your reference point is, which is the linear slope. Okay, how are we doing? Thumbs up, thumbs up. Other questions or clarifications? Okay, let me show you what it looks like to get something like this in programs. So in example 4, part 2, so I have page 7 up here. We started going over this last time as well, but I'd like to go back over it since the stream didn't capture it. Looks like the stream's still good. Where's my chat window? Okay, no chats, that's good. All right. So as usual, there's a lot more here than you necessarily need to pay attention to at any one time. Part 2 of example 4 has 3 different sets of models in it. One is the quadratic set, one is the piecewise set, and the other is for an ordinal outcome that demonstrates another use of piecewise. So the part I want to direct your attention to in terms of how you would go about doing section 2 of homework 4 that asks you to do a quadratic model is right here. So you would need to center the predictor if the instructions asked you to. So I believe in this case, and let me pull up homework because I opened it up just to make sure. So this is homework 4 that I have scrolling by. Okay, so in section 2, enter a model predicting number of strokes taken, so golf scores the outcome, from linear and quadratic slopes for enthusiasm, in which enthusiasm is left uncentered. So that means uncentered means you can skip that step. You don't need to make any new variables to be able to do this. You don't even need to make the squared variable because you can do that on the fly within the model itself. So you can skip all the data manipulation stuff. These are describing the variables and the code to make all the pictures. We went over the linear model last time, so let me start with the quadratic model because this is the only one that you need to do section 2 of homework 4. So enthusiasm is the variable that you would be using instead of age, but it's synonymous. So age has been centered at 18, so that the reference point for this, we're predicting personal income, is the lowest age that I have in my sample, 18-year-olds. So the syntax here, if you want a bunch of pictures, by executed every single time. So personal income in $1,000 units is my outcome variable, and I am saying that that is going to be a quadratic function of age. Now note that even though what I'm calling it is a quadratic function, it has to have both the linear slope and the quadratic slope. They both work together. Because the quadratic is going to be above and beyond the linear has to be there with it to be interpreted, for those to be interpreted correctly. So in SAS, make this a little bigger, maybe. Oh, come on. All right, maybe not. It's this thing right here is an asterisk. That is used to define an interaction between variables in general, but more specifically here, it's an interaction of age by itself. So that is age squared. You don't have to make it as a variable in your data set. It gets made in the context of this model. The analog to that in Stata. So Stata code first is always the outcome variable. I've helped several people with this. Don't forget that. Order matters. Outcome variable is always first, just like it's first in SAS. And then after that are the predictors in your model. And instead of an asterisk in Stata, the quadratic effect is defined as a hashtag or a pound sign if you're old like me. You can take your pick. Then comes the comma. So if you were to need standardized effects, you could also add the word, just a second, I figured out why my keyboard isn't working because I haven't turned it on yet. You could add the word beta here if you wanted to get standardized slopes. I didn't ask for them in this particular homework, but you can do that. There's only one comma that you need. So there's not commas between the multiple slopes, it's only at the end. I'll take that out just for sake. These statements, these lincom statements, you don't need these in your homework. I included them in there for your future reference as to how you would ask for either a predicted outcome from your quadratic model or a predicted linear slope for any particular value of your X predictor. So here I'm demonstrating how to use these to get what at age 30 the income would be predicted to be and what the slope would be at age 30, at age 50, at age 70. But I'm not asking you for this in your homework. Likewise, there's some extra stuff in here that you haven't seen before. This line right here, output out, you don't need that either. What that does is save pieces of output as SAS datasets so that I can then access them and do math on them. I did that in order to create columns of predicted values so that I could make pictures. You don't need to do that, so you can just disregard that part. Okay, questions on the setup of the model to fit a quadratic effect? Okay. Mm-hmm. Right here? Okay. Um, so the order is the same as if it were in the equation. The first variable optim model is the outcome. So this is score, yeah, in this case, equals, and then this would be the enthusiasm is the name of the column. So it's a individual differences measure of enthusiasm towards mini golf, the guess, and that'd be squared. You do need that part. You need it'd be score equals enthusiasm, and then enthusiasm times enthusiasm. Yep, yep. hmm You need both of them. The linear and the quadratic effects work together to make the whole function. Sure. Yes, the enthusiasm scale is called the MGUESS, the mini golf enthusiasm scale, because most of the time, if someone asks you, "Do you want to play mini golf?" Guess. So, come on. I'm here all week. I'm here forever. Yeah, I guess. Except for me, I'm like, no. Hard no on that one, thank you. But some people take mini golf really seriously. Thank you. Yeah, I'm here all week. I'm here all year. If I'm here all summer. Anywho, enough whining. All right, so here's the output. Then we have this part right here, the first set of results. That's telling you about your model. So does the sadistics. Badoomch. You guys are funny too. I like it. Yes, internet, if you're listening at home, my kids are making puns. So we're talking about sadistics. That could either be sadist or sad. Maybe a little bit of both, right? Eh, if the truth fits, right? The shoe fits if the truth fits, something like that. Anywho, this is my model. So, big picture question here. Does age predict income? Like, that's what we want to know. Based on the patterns of the means for income at each age, it looked like it needed to be a curvilinear function. So to fully capture a curvilinear relationship between age and personal income, we need two slopes. We need the linear effective age, we need the quadratic effective age. So that's where for this model line, degrees of freedom, this is numerator degrees of freedom, is 2. It's the number of slopes in your model. Sums of squares is the amount of information captured by those slopes. More specifically, it's the difference between each person's y hat, the predicted outcome, and the mean. So like how much more customized the prediction of income was than just giving everybody the same based on their age. If you take that amount of information, sums of squares, and divide it by 2, you get this column right here. That's your mean square model. That's like how much information did the model capture per slope. So I'll say that again, since I see everyone's writing things down. Sums of squares is information, generally speaking. Sums of squares for the model is how much information in income was captured by the model, was explained by the model. And I'm saying information because it's not variance. It's the numerator of a variance equation. It's how far off each person's y hat is from the y hat minus the mean. So how much extra customization in the prediction of income did age give you relative to just giving everybody the mean income and calling that enough? If you take that sums of squares model and divide by the number of slopes, numerator degrees of freedom is 2, you get this mean square right here. So that means how much information has been captured per slope. Okay. Ready for the next line? Okay. So error, synonym for error, residual. That's what it's called in Stata, and that's the term that I generally tend to use. Is what's left, right? What don't you know? Well, I could put up to 731 more slopes in this model. That's based on my sample size. This sample is 734 people. So far, I've estimated an intercept, a linear slope of age, and a quadratic slope of age. So I've spent 3 things, I've got 731 left. Now, how much information is left? So this is quantifying how far off our prediction is for each person from their real outcome. It is their real outcome minus their y hat in squared terms. So just like we down-weighted information explained by dividing it by the number of slopes it took to explain it, we do the same thing for sums of squares error. We divide it by the number of slopes that we could have estimated, and that gives us mean square error. So sums of squares error divided by denominator degrees of freedom is what the number of slopes you could still have, the 731 is. That works out to be mean square error. That has a special name. Homework question. What is it? I'm eagerly looking at my chat window. Or you can just unmute yourself and use your words. Mean square error has a special name that I ask you about at least 3 times in this homework. Yeah, residual variance. So variance left over in income that is not explained by age. So then last but not least, how much information did we get per slope divided by how much information is left divided by per slope left? That gives us our friend F. 47 is good. One of you wrote that on your quiz, like 42 is good. Like, yes, 42 is very good. 42 is also, I believe, the answer to the universe, right? Is that book? Someone, yeah, I'm dating myself again. 47 might be the answer to the universe, but 47 in this case is different than what F is expected to be. I don't know what the critical value is because for F, it depends on numerator and denominator degrees of freedom. It takes a different shape, but F is in a squared metric. 42 is good. Yes, 42 is good. 47 is great also. So F is always going to be positive. The reason for that, in general, what F is testing is the two slopes put together. And so we need to make sure that it's a squared unit. That way, one slope can be negative or positive and they don't knock each other out. The p-value that comes next to it tells us that, yeah, 47 is unexpected. That's way out in the tail. If these two slopes together didn't account for any information or none more than would be expected by chance, then your F would be 1. One's sort of the theoretical minimum. But it's 47, so it's way significant. Another technical term, way significant. So what we know then, the model is significant. Age explains a significant amount of variance in personal income. But we don't have an effect size yet. So for every time you say significant about a decision, you got to give them an effect size. Because as you can see from the degrees of freedom, this test statistic has both effect size and sample size embedded in it. That helps us determine significance, but we also need effect size. So do you remember what the effect size is that goes with this F? It's another letter. D. D would be per T, not an F. Yeah, R square. Yep. And it has to be R square. Obviously, you can take the square root and make it R, but since F is in a squared metric, it sort of lends itself to R. D squared is not a thing, but R2D2 is a Star Wars character. Touche. You guys are on a roll today. So here's our friend R square. There are 2 ways to interpret R square. Do you remember this? Not off the top of your heads yet? Okay, let's do it again. So R square, one way to think about it is as a proportion of variance. Of all of the reasons why some people make more money than others in this sample, 11% of that is attributable to their age. So 11% of the total variance in my outcome variable, which is money here, has been explained by my curvilinear function of age, my 2 slopes for age, linear and quadratic, working together, 11%. How much is left over then? Don't think too hard. Yeah, 89%, exactly. A lot. Also true. In the social sciences, it's pretty rare to see anything more than like, I'd say 20% in an R square. Like these are tiny things usually. The more people you have, the smaller your R square can be and still be declared significant. Just keep that in mind. We got a lot of people here. We got 734. So yeah, 11% of the variance has been explained by age. 89% remains. That's what we know. The other way to interpret R square is to think about it in terms of y hat. So y hat is the predicted income for each person based on their age. So if I were to calculate y hat for each person, and by I mean SAS, that's actually what's happening in this line right here. I am making a new data set and adding a column that has the predicted incomes for each person. I named that variable y hat for age, and I also asked for the standard errors for those predictions. So if I were to make a column in my data set, predicted income based on your age, right? I've got another column that already is their regular income. So what should have happened, what did happen? What shoulda is y hat, what did is y. Both of them with an I subscript because they're individual specific. The correlation between y hat, shoulda, and y did squared is R square. So if you take the correlation between predicted income by the model and real income and square that correlation, that is R squared. In practice, I would say people tend to use the first definition a lot more. The 11% is the proportion of variance explained. That's much more common. But I will say the latter definition generalizes to models that have more than one source of error variability, which is what happens when you have observations that are correlated from the same sampling unit. So you can take my other classes if you'd like to hear more about that. Okay. Questions on any of that so far? Okay, then let's look at the output. So the extra stuff that I asked for in the estimate statements, the predicted income at various ages and the predicted linear slope at various ages is here. Here's the part that you would get and that you would need to do your homework. These are the fixed effects in the model. There's 3. So the intercept for the first row, the linear slope of age in the second row, and the quadratic slope for age in the third row. So the first column is your estimates, labeled as coefficient in stata, and intercept is labeled as underscore const for constant in stata as well. Standard error for is always, you get to answer this question like 17 times in your homework, and in the last homework too. Standard error for a slope, how far off, on average, the sample slope is from the population slope, where smaller is better. If I take my estimate for each of these divided by the standard error for each of these, that gives me my friend t. So t then is going to be compared to a t distribution with denominator degrees of freedom for the model, and it can tell me in a more standardized way how unexpected each of these slopes is if the true slope were 0. Note that t is signed, so we're testing one thing, like for instance, this quadratic slope is negative, therefore the t is negative. So that tells me that it's significantly negative. The t is positive for the intercept and for the linear slope, so then that we know that those coefficients must be positive. Okay, and then we did this in class last time. When we get all the way done with the handout, I'll post this version that I've been taking notes in. But intercept, always the expected outcome for when the predictors are 0. In this case, that's the expected income for an 18-year-old. The model then describes relative to that 18-year-old reference point what happens to it it goes up at first. So the slope at age 18 is 1.2. So that means as evaluated at that part of the curve at age 18, for every year older you are, you make $1,200 more dollars. But that's not constant. It's not like $1,200 a year for the rest of your life. The quadratic is working simultaneously to take that positive slope and slow it down. So this combination here of a positive slope of age at 18 paired with a negative quadratic coefficient for age squared, that's a less positive. Yes. I think I'm backwards to you guys. Maybe I should be doing it this way. Does that work? I have no spatial reasoning. I can't do it. Yeah. This way? Does that look righter? Okay, I'll try and do it backwards. Yeah. So yeah, it's a positive slope, but it's becoming less positive. And I think I've got pictures here coming up. I have it actually graphed out what it looks like over the trajectory. But what's happening to the linear slope right here of 1.22 is becoming less positive per year by twice this quadratic slope coefficient. So it's slowing down by about 0.04, less positive. And yeah, here's some pictures. The picture on the right, the nice smooth trajectory, is what the model predicts. So yeah, down at 18 here, there's a positive slope, but it's slowing down as age increases. And you can actually calculate the point where it switches directions, and it works out to be around age 48. And then from there, age has a negative association with income. 0.04 is me rounding this number right here and multiplying it by 2. Yep, so the positive slope of age at 18 is becoming less positive by twice the slope for the quadratic term, so twice the 0.02. So if someone were to ask you, hey, what did you find in your analysis? Is age related to income? You'd have to say, well, yes, it's related. 11% of the variance. And they're like, oh, so do older people make more money? Well, ish. Like, if you're 18, a person who was older than you, like a 24-year-old, makes more money. But if you're 62, a person who is older than you, like a 70-year-old, makes less money. So there's some nuance here that you would have to use in trying to describe these effects. Making a picture is probably the easiest way to do it. So the picture on the left is spit out by default when you run GLM. The one on the right is the one that I made with all of this extra code. Okay, last piece on this. How do I know if this R square of 11% is better than the one that was in the previous model, which we looked at last time, which was linear? So if I just had a linear effective age, that accounted for 4% of the variance. By adding a quadratic effect, a squared term, as a new predictor, I went from 4% to 11%. That's a net gain of 7%. How do I know if that change in R square, that increase, is significant? It has to be the direct result of whatever new predictor effect was entered into the model. And in the situation like this, where the models differ by only one term, if that new one term is significant, then we know that the change in the R square is significant. So the analog to this you guys already did in homework 3. In homework 3, for one outcome variable, let's say fits thrown, I had you start with an empty model, right? Remember this? Or have you blocked out homework 3 already? Not yet. Yeah, that's coming. So homework 3 started with an empty model. An empty model has no predictors in it. Yes. The empty model gives you back the mean of the y outcome variable as the fixed intercept, and the residual variance from the empty model is all the variance that there is to be had. It's like a jumping off point. And I asked you, after adding pleases, number of pleases heard and predicting number of fits thrown, whether the change in the residual variance was significant. And for all of you, regardless of what your individual data set had, the model, after you add a predictor, had less variance in it. The question is it numerically less or significantly less? And the answer depended on whether or not the predictor that you added was significant. So if you found a significant slope for pleases heard in predicting fits thrown, that significant slope in turn means that the amount of variance that's been reduced is a significant reduction. So if I go from no predictors to one predictor, that one predictor means that if it's significant, the difference in the variance is significant as well. If the predictor were not significant, if the slope were not significant, then even though the variance might be lower, it's not significantly lower. So by that same logic, if I go from empty to one predictor to two predictors, if the amount of variance that was explained goes up, meaning the amount of variance that is left over goes down. So you can, it's contradictory in direction, right? If r squared goes up, that means your variance that's left is going down because it's being explained. So if r squared goes up after you add a second predictor, then the result for that second predictor specifically tells you whether or not the model now explains more variance significantly than it did before. So in this case, the second predictor that I added is this quadratic effect of h. It's significant. So that means, depending on how you want to say it, the amount of variance accounted for by the two predictor model is significantly more than the one predictor model. The 11% r square is significantly more than the 4% r square. Or the total amount of variance that's left has gone down significantly. So as r squared goes up, remaining residual variance goes down. It's the same concept, just said differently because of whether you're counting what's left or what you have. Now, one thing we haven't talked about, which is coming in the next unit, is what happens if you go from a model, say, that has one predictor to three predictors. Well, then you have two new things at once. And that means that any change in r squared could be because of one of them, the other, both, or them in combination because they may be related to each other. Then you may have to ask via a specific command, which is known as contrast in SAS or test in Stata, whether the reduction in residual variance or whether the increase in r squared is significant. So we'll get there eventually. Okay, how are we doing? Do you feel like you can do this? Not yet? So just to remember, no new variables, section 2 of homework 4, one model. Outcome equals linear predictor, and then linear predictor times itself to make the squared one. That's it. You can ignore the rest of this. Okay. Other questions before we change gears a little bit and look at piecewise stuff? No? No? Okay. Then we're changing gears. Let me get my PowerPoint back up again. So we did quadratics, and there's those solutions. So this is just the same results that we just went over. Exponentials, these is another type of curvilinear relationship that you can get by putting in a log transform predictor. This is just sort of an FYI for your future reference, not something you're going to do. Now to answer Melissa's question at the top, piecewise models. We haven't talked about these yet. This is another way that you can describe a nonlinear effect of a quantitative predictor, but you do it by grouping it into sections. So I have this this picture up here. This is a plot of the means of income per unique year of education in the data set. So the way it was collected is discrete. And the black line shows the means, and the red lines show the standard errors around the means. So there's a lot fewer people who didn't graduate high school. That's why those standard errors are a little bit wider, and then they narrow as you get into more common levels of education, and again, widen as you move out. But in example 3, we fit a linear effect of education and asked, do families that make more money, is that related to the education level of the respondent? Well, this is personal income and personal education, but as you guys well know, there's not the same effect of education all along the possible years, right? Like if you get up to 11th grade and you don't graduate high school, your job prospects are probably not that different than if you had dropped out at 8th grade, right? Like high school degree or GED is a threshold that matters. Likewise, if you went to some college and you didn't complete an associate's degree or a bachelor's degree, then functionally you just completed high school. And for those of you working on PhDs, ABD is not a thing, right? It's not a thing that like will get you an extra job, right? It's a set of letters that doesn't work. It has to have the PhD to count, right? Yeah. So going through all of these extra grades doesn't count. It doesn't help you unless you actually finish. So none of that was accounted for in our previous analysis. So I want to teach you how to do something like that using education as an example. So I categorized education years in as sort of 3 discrete levels. There's less than a high school degree. There's the bump that you get from graduating high school. And then there's anything after that, which looks like it's sort of curvilinear in this case. More is better. So this idea that there's a different effect of education before you graduate high school, if you graduate high school, and then after graduating high school, that lends itself to a model that has 3 predictors in it to try to capture the slope for education in those 3 different regions. So here's how I'm going to do that. I'm going to take my original predictor of education in years, and I'm going to carve it up and make 3 new variables. In your homework, you are going to do the same thing with experience playing mini golf, but you're only going to carve it up into 2 slopes. So it's a little bit simpler than this example. So I have on slide 30 here a data set that would show what the original variable would look like on the left-hand column here, years of education, which is my X. And then here are the 3 new variables that I'm going to create. And I'll show you the code to do this in a second, but I wanted to show you the logic first. So I have declared grade 11 as my reference point, my intercept. So that's where all 3 of my new variables, these are new predictors that are going into the model, are zeroed out, is in grade 11. My first column here, called less than high school, this is going to capture the effect of education specifically among people who never graduated high school. So it starts at 0 and it goes backwards because 11th grade is my reference point. So if you have less than an 11th grade education, like if you have a 10th grade education, it's -1. And if you have a ninth grade, it's -2. If you have eighth grade, it's -3, and so on. So this captures the effect of one more year of education up to a point, up to 11th grade. The next column then, grad high school, is the acute shift, so to speak, a bump that you get from graduating high school. So it doesn't turn on, so to speak. It stays at 0 until you hit 12th grade. Then it switches from 0 to 1. But because this predictor is only capturing the acute bump of graduating, it stays at 1 after year 12. So it sort of jumps up and then shuts off. It shuts off, and then the third column picks up where it left off. So then amongst people who graduated high school and then went on, what is the effect of additional years of education among people who went past high school? So if you only went to high school, you're 0. If you went to 13th grade, you get 1. 14th grade, you get 2, and so on. And so I'm dividing years of education, this x-axis, into 3 sections, so to speak. And I'm fitting a separate slope for each of my 3 sections. So this type of model, I call it piecewise slopes. It's because it's like you have your separate pieces. The original slope has been chopped up into sections. It's also known as linear splines. So that's another word that you may hear to describe this type of model. I find these models to be really useful when you have predictors where not all values are equally meaningful, right? So let's say that you have something like a cutoff score for depression. If I remember correctly, like the CESD is like if you get 16. Does that sound right? Any clinical people in the house, Jacob? Am I just making shit up? Yeah, a little bit. I think I'm confounding a few things together, but I know there are scores at which, like, if you hit some number, like if you're after that number, you're labeled as something different, right? You either have a problem or you're gifted or there's some classification. So for anything that works like that, having a separate effect of the variable sort of before you hit that point and after you hit that point could help to sort of empirically test whether or not that breakpoint is something magical. So if you found the same relationship of a variable sort of before the magic breaking point and after, that would speak to the breaking point being somewhat arbitrary. You may also hear about these sorts of models in the context of regression discontinuity designs. That's a specific type of quasi-experimental design where you can't randomly assign people to groups and you're stuck trying to work with that in a real-world setting. So these models show up in that context as well. They also show up in what's known as SMART designs, which are randomized control trials where halfway through they see if people are getting better, and if you're not getting better, they reassign you to something else. So these are used a lot in sort of real world research designs where you can't control everything. Okay, so is the coding, or excuse me, not the coding yet, the pattern, does this make sense? Sort of the big picture idea is that we're splitting this one variable into 3 sections. And it starts sort of at the beginning here. The first section runs from up until grade 11. The second section runs from grade 11 to 12, and then it shuts off at where it left off. And the third section picks up where it left off to track further changes in education. So 3 different linear slopes. Now, how do I do that? The code for each of the programs is right here. So it looks kind of similar to what you had to do to code groups in homework 4. If the original variable is this, then make new predictors with these values. So we'll do SAS first. If education is less than 12, then my first column is going to be the original education variable minus 11. So it's 11 because that's where I want my intercept to be. So if you're talking about somebody who went to 11th grade, then this whole row will zero out and they'll become my intercept. 11th grade education is sort of the reference intercept for the model. Otherwise, so this is a question I think Melissa asked last time, the else. This is just a coding thing to make it faster as it rolls through your data set because it wouldn't read these next sections if they've already answered yes to the first if. You don't technically need them though. So otherwise, if education EQ means equals, then the first slope is 0, the second slope turns on, switches from 0 to 1, and the last slope is still 0. So if you have a 12th grade education, you get the bump for having that, but you don't get anything else relative to an 11th grade education. Otherwise, if year is greater than 12, so among the people who went past high school, so it had to be at least 13 to get into this if statement. The first slope is not relevant to them. They get the bump for having graduated high school, and then their third variable picks up where high school left off. So how many years past high school did they make it? That's what this over high school variable is going to become here. And don't forget your ends, which is the matching to the do's here. So the do makes it so that you can do multiple things at the same time within the same if, and end is what shuts that off. So in Stata, I'm setting each of the variables equal to 0 to start with, and then systematically changing their values. So if it's somebody who is less than 12, then I'm going to change the first one here. So education minus 11 is what's going to go into my new variable less high school. If somebody is greater than or equal to 12, then I want the second one to change to a 1. So that picks up these two right here. And then if they're greater than 12, then the last one is going to pick up how much more they have than 12. So it looks a little different, but it's doing the same thing. Okay. Does that make sense? Can I go over any of that again for you? Good so far? All right. Then here's what's going to happen. In the output, since we're running out of time, I'll just show this and then I'll show the coding scheme last time. So here's what my model looks like. So I have one predictor conceptually, which is years of education. Like that's the idea of what's predicting in this model. But rather than putting years of education in directly, I'm putting in the 3 new columns that I just made. So beta 1 is going to capture the effective education, the slope for education for people up to 11th grade. So that's 11th graders are the beta 0. Beta 2 is going to capture the bump of going from 11th grade to 12th grade. And then beta 3 is going to capture the extra effective education after 12th grade. So in this case, I'll add the space here later. I forgot to do that. The model F has 3 degrees of freedom in the numerator because I've got 3 slopes. If I had 4 slopes, how many degrees of freedom would I have in the numerator? 4. And if I had 5 slopes, 5. Yes, that's what numerator degrees of freedom means in this model test. 730 is denominator degrees of freedom. That's how many more slopes I could add based on my sample size. My F value is 47, again, very big. MSE, that's my residual variance, is 159. The p-value that goes with this f means that this f is really unexpected. So the slopes work together to capture significant variance in this outcome. How much variance did they get? 16%. So 16% of all the reasons why some people make more money has been captured by these three different slopes for the different sections of years of education. And so here's the solution that we end up with. If you have an 11th grade education, you make $8,000 a year. If you have less than 11th grade, the slope for each year of education is actually not significant. It's negative, which is sort of funny. It means more education is bad, but it's not significantly different than 0. So the p-value is 0.6. If the true slope were 0, we'd get a slope of this number 60% of the time. That's definitely in expected territory. So that means conceptually, if you have less than an 11th grade education, it doesn't matter how much less. Slope's flat. Beta 2 is the effect of graduating high school. That is significant. So that is the difference between an 11th grade education and 12th specifically. That's a jump of about $4,600. And then after that, after 12, the slope is 2. So it's another $2,000 per year after grade 12. And that is also significant. So putting it together, if you don't graduate high school, it's not good. If you graduate high school, that helps. If you get more education than a high school degree, that helps more. And these three effects work together to explain significant variance. Here's the picture that they make. So the slope before grade 11 is flat. It's negative, but not significantly negative. There's an acute shift up to grade 12, and then the slope out here is significantly positive. So two positive slopes of different magnitudes here. All right, how are we doing? So we are about out of time. Any questions before we adjourn for the day? And we'll pick this up next time. Not yet? Okay. I think next time it would probably be instructive to try and work on how to set up the coding for section 3 of your homework. We can do that together, but give it a shot. See if you have time, give it a shot on your own and see if you can figure it out, and then we'll work on it together next time. Okay? There. Then we won't have sadistics, either sad or sadism. All right, then I will sign off for now. Office hours at 3:15. If you need anything, let me know. Okay? Cool. Peace out, everybody.